question is about writing the market network only in these three variables here, the x's, and then second is thinking about what loses in terms of information. So you want a market network of the distribution of the x's only. So the way I would approach the question, actually, I guess there's a couple of ways we can do it. I would actually write out what this thing is and think about what that tells me about the links between the variables. So we know that this belief network describes a joint distribution in all of these 5 variables, which is given as this factorized form. So it's x1 given h1, x2 given h1 and h2, x3 given h2, and then h2 with no condition. And then to get from here to here, we need to sum out over h1 and h2. But actually, what you notice is you can distribute these summations over this thing, or you can distribute one of them. But you can never uncouple the thing into separate factors. So actually, what you find is that by doing this, links all of the variables together. There's no factorization of this thing that simplifies it. And so what that means is that the market network is just completely connected in the 3 variables. So this is a market network for the 2 variables. There's no way to separate the factors in this thing. And so the next question really is about the link between this representation and this representation. The question is it a perfect map of this distribution? And the answer is no. And the reason for that is because going around in the system. So the question is it a perfect map? Of this joint distribution? The answer is no, and that's because if you think about marginalizing out x2 here, so think about this joint distribution x1 and x3. Well, actually, you can show that this thing is these guys are actually conditionally independent. x1 and x3 are conditionally independent. So let me show you that. So this is the definition of modularizing variable, and then actually we can. Using this thing, write this whole thing out. So this is going to be a sum over x2 and a sum over h1 and h2 of this whole joint distribution. x2 given h1 and h2, x3 given h2. But actually, this thing factorizes into factors in x1 and x3. So I can write this as a function in it's 2 separate functions, or 2 separate functions in x1 and x3. So I can sum this out, this x2. This is just a definition of modularization. So if I sum out x2 here, this just becomes a factor of 1. Yeah, so I can get rid of that from my function. And now it's pretty obvious to see that I can factorize this into 2 separate factors, one in x1 and another one in x3. Just write it like this. x1, here h1, and here h1. And now because there's no h1 in these factors, I can separate them out into this separate term. Okay, so what I've shown effectively is that the joint distribution of x1 and x3 is exactly the same as here x1 and here x3. So x1 and x3 are independent, actually, in the original representation. But under this Markov network, they're absolutely not independent. For two reasons. One, because we've got a link already between the two. The second, if we condition, or sorry, if we marginalize x2, which is what I did here, it introduces another link. And you can see that actually in David's book. So we've got this nice so it shows you here the second one. If I marginalize over this C, if I have this Markov network and I marginalize over C, it actually introduces a link between the A and the B, and that's effectively what I'm doing here. If I marginalize over x2, it introduces an additional link. So the Markov network does not include or describe this conditional independence of x1 and x3. So the answer is it's not a perfect map. Question 4, 7 part 2. Okay, does that make sense? Everyone sure what I'm talking about? Okay. The next question is 4.10. And question 4.10 says, considering this distribution in x, y, w, and z, and then we're interested in whether basically x and y are conditionally independent conditions on z. So let's go through that. I'm going to write out a belief network for this thing. Okay, so we have this joint distribution in x, y, w, and z, which has a belief network. It has x and y being not conditional on anything, and there's telling us something about w, and w tells us something about z. And the first part of the question says, write down the formula for x to z. Okay, so this is very similar to stuff that I took me through last time I was here. So, definition of conditional independence of this thing is just the joint of x and z divided by the marginal of pz. It's just simple definition of conditional independence. And then all we need to do is to calculate these two factors. Well, the denominator, or the numerator, dxz, well, this is just calculated by summing out from this whole joint distribution variables we're not interested in, which are w and y. From the joint. So we've got z given w given x and y. X and y and 0. So when you write something down like this, your first question is, can I simplify it? And what do I mean by that? Well, first of all, do any of these variables just marginalize so that I can just cancel the factor as I did up here with x? No, absolutely right. So the next question is, well, can I distribute the sum through the thing? And well, yeah, I can. I mean, I can distribute this, the y, to sort of here, beyond the first factor. And of course, don't forget that I can reorganize these factors a little bit, but it's not really going to help me very much here, because I can't push them all the way through. So that's the numerator of this thing. The denominator, well, I just sum out z from this thing as well. And so the answer is, for the first part of the question, this numerator, z given w given x1, x1, divided by sum over w, y, and z. Okay, so we can't actually simplify that at all, I don't think. So for the second part of the question is to say, well, fine, what's the same thing but with y instead of x? And you know what? This is dead simple because it's just if you think I could just relabel them, right? And it would just be the same. So basically the answer is the same thing but with x's instead of y's. And y instead of x's. So it's just basically the same. Okay, I think that's pretty simple, hopefully. Then the final part of the question is, using those two results, can we decide if x and y are conditionally independent, conditional on z? And so, definition of conditional independence is that the joint of the two things, conditional on z, because we're interested in conditional independence, conditional on z, is equal to these two guys. We'll come together. The question is this true? Question mark. Well, you might be inclined to think no. I would be. Actually, that's the right answer. Then this is not true. So how can we see that? Well, what I would do is write down the formula for this, and see if I can factorize it into the things that I know are the marginals. So let's write down a formula for px, y, and z. And it's just the same thing, right? We use the definition of conditional dependence. So on the top, we're just going to marginalize out w to get this joint. So there's going to be some w with the same factors. And sorry, this did anyone spot my deliberate mistake? You should have shouted out. Sorry, that's my that should be x, and that should be y, right? So these should have the same denominator. Yeah. So it's going to be the same denominator here as well. So my question is this thing equal to this times this? And well, let's forget about the denominator because it's the same. So the question is it true that this numerator times this numerator equals this numerator? y is in square brackets times y, and anything with x here. Is equal to typically only something with w. The x, the y, with w. And basically, you're never going to show that. You're never going to show that these guys are equal. So x and y are not conditionally independent, conditional z. That's the question. Everyone happy with that? Okay. I'm assuming you've all written what things are right because we're running out of room. Okay, next question. Source well. So this is again about a Markov network. So we've got this Markov network in A, B, C, and D. So I think the first part of the question is to draw a Markov network for this thing. Luckily, it's quite simple. So there's only 4 factors. We've got 4 variables, A, B, C, and D. And so we've got a factor in A, B, factor in B, C, factor in C, D, and factor in A, D. This is the simple 4-cycle. So it says, explain if the distribution can be represented as a non-complete belief network. Okay, now the answer to this is, well, David's answer to this is quite subtle, I think. So you probably remember that when you have a belief network, it describes a joint distribution, but actually you can change the direction of the arrows without changing the meaning of the distribution. So I think David had a nice sort of picture of this somewhere. Chapter 3. Here we go, this one. So these 3 graphs all express the same conditional independence assumptions. And so basically we can turn the arrows around. And what this tells us is if there is a belief network that's non-complete and that represents this distribution, then there has to be what I call a collider. Okay? And a collider is a node, let's call it X, which has arrows coming in from 2 directions. So if there exists, so this is the second part of the question. Yeah. Does there exist a belief network? Well, if there exists a belief network, it has to have a collider. Okay. And if there's a collider, so if any of these variables is a collider, then I can marginalize that like a collider, and that makes the things that were coming into it independent. And that's something that you already know from chapter 3, hopefully. So if I have something like this, let me pick some other variables. If I marginalize x, then y and z are independent. Okay? But it's definitely not the case that any of these, if I marginalize any of these variables in a belief network, well actually that creates another link. Right, if I were to marginalise out C here, you would create a link between B and D. And it's the same for all of them. So there's definitely not a belief network, because if there were, I'd have a collider, and in order to marginalise a collider, they would be independent. But if I'm marginalising a variable, they're definitely not independent. Does that make sense? It's not a trivial argument. Let me go through it again.
Can you explain again why there would have to be a collider?
So a belief network it would look like this, right? Because there's links between all of the variables here, but with arrows on, right? So I could have a cycle, which would be a complete belief network, right? So if it's going to be non-complete, then one of the arrows has to be the other way. Yeah, so it has to be a collider. Does that make sense? And if I were to marginalise that, then it would make things independent. But I know from the from the marginal network, that if I marginalise any of the variables, it puts a link in. Yeah? Does that make sense? Right. The third part of this question. Sorry, looking in the wrong place. Third part of the question is to derive explicitly if A and C are conditionally dependent. So this is again a definition of conditional dependence. So we want to know if the joint of A and C is equal to the product of these modules A and C. That's our question. Well, let's take the joint on the left first of all. So this guy is, you guessed it, it's the sum over B and D. The joint distribution, which was the thing with the finite notes. So this is going to be phi AB, phi AC, phi CD, phi BA. Okay, simple. The question basically is, can I write this in some function in A times by some function in C alone? And actually I can't do that. There's no way I can do that because they're joined together by the summation over B and D. So I can't do this. Basically, it's difficult to know what more to sort of write here, right? I mean, you could push the sum of D to here, and then you've got two things, but each of those factors maybe like this. So I could write this as a sum over B, phi AB, phi BC, times by the sum over D, phi CD, phi BA. But this thing is a function in A and C, as is this. So there's no way I'm going to couple those factors. So that's question 412. Sorry, I should probably write a question. Okay. So I think that's all of the questions in chapter 4. Right? Yeah. Okay. So now on to chapter 5, which is all about efficient inference. And so the first question from chapter 5 is 5.1. Okay. So question 5.1 says, we have a pairwise singly connected Markov network with this hidden swarm. So it is probability of the things x. I actually don't like David's notation here because he's a bit sloppy with his x's. It should be really a vector because there's lots of x's. 1 over z, because z is a normalization constant. And this product I twiddles j by xi xj. So basically, this twiddles just sort of means that there's a link between I and j, right? Wherever they are. So we've got this product of factors between two x's. It says explaining how to efficiently compute the normalization factor. So we want to compute z. As a function of the potential phi. Normalization factor z. Okay, so z is just going to be. Anyone take a guess? Alright, so what we need to do is sum over all of the x's, right? Of this thing. So take out the z, sum over all of the x's. And actually, if you want to be strictly correct and derive that, okay, what we know about a probability distribution is that it sums to 1. Right? So we can write first of all that this 1 equals the sum over all of these x's px. A simple factor probability distribution, right? We know that this is equal to this, so we can write this as the sum over x and 1 over z. This product of things making I and j. Okay, and so now let's modify both times by z. I have that z equals this thing. Okay, which is what I was going to go straight to. So how do I calculate this thing? I'm told that the Markov network is, what was the phrase, singly connected. And this is the key phrase in the question. So because it's singly connected, there must exist a node which has got at most one edge. Yeah, or else there would be a loop somewhere. Okay, so there exists x, let's call it E, with at most, excuse my handwriting, one edge. Okay, so then let's rewrite this thing as some sum over all of the things which aren't xe. So let's call this, I don't know, less xe. Okay, so sum over all of the x's which aren't xe. I'm just going to write this big sloppy hideous thing, which basically means all of the product of all of the factors that don't include xe. Okay, and I've already said that xe has at most one edge, so that means that there's only this one factor which has got xe in it. And let's call its neighbor xn. Okay? I can definitely write this.
Doesn't it miss the product?
I've just wrapped it up in this thing that I call find rest. So that the product is in here. So I've just taken out one of the factors, put it here, and the rest I've just called this. Yeah. So what we need to do now is let's call this thing, never really sure what letter this is, that. We're like phi or something, right? That's right. It's capital phi. Psi. We did that. Xn. Okay, so I can calculate this for every value of xn, and this is just another thing. There's only now an xn because I've summed out xe. Xn is the name of xe. But actually, you know what? I can just write this term into one of the potentials in xn. Yeah, I can just hook this up with one of the potentials in Xn. And what that means is I've now got a graph with one less node that's still singly connected. Is everyone happy with that? Yeah, because I've got rid of XE by marginalizing it out. I've wrapped up this factor into one of the potentials in Xn, doesn't matter which one. So yeah, I've got a graph with one less node that's singly connected. So I just do the whole thing again, and I keep on doing it. Okay? And that means that I have an algorithm in principle which scales with the number of nodes. You're looking at me. So basically that means that the amount of effort required is just constant times by the number of nodes that I have in the graph originally. Okay, so that's the answer to that question. I think that's all. Yeah. Okay. The next question is 5.2. And this question this question is actually quite subtle. So, basic question is all about loop cut conditioning, which is a method of using a factor of Markov networks to be able to compute something that looks like it's very difficult, but actually there's an efficient way to do it. So somewhere in So considering this pairwise Markov network on binary variables, that word's also important in this question here, 5.2. Do this. The first thing I'm going to do is draw this Markov network. So we've got 100 variables, I'm not going to draw all of them. So we've got x1, and that hooks up to x2, that hooks up to x3, so on and so forth, until we get to x100. Then x100 and x1 are connected. So we've just got this big loop. And actually, what we're interested in doing we're actually calculating the argmax over all of x's at the x. Okay, so we want to calculate this thing. And basically, this should be difficult. So if we sum over any one of the variables, so let's say we sum over x1, you know from having read the book constantly that if we sum out over a variable in a Markov network, this is a chapter before, right? Yeah, right. So if we sum out over one of the variables in a Markov network, this is marginalizing, then it introduces a link between the two things that connect to it. So if I sum out over one of these variables, then it introduces a link, and so the whole thing is connected. Which is a pain, and would mean that this thing is very difficult to compute. But the insight here comes from the fact that if I condition on any one of them, then there's no link introduced. Okay? So this comes directly from this illustration here in the book, right? So if I condition on any one of them, then those two things are then not linked, and I just have a straight line, I just have a chain. and I can do efficient inference over a chain. So that's the real insight here. So let's say we condition on x1, for example, arbitrarily picked, then this thing just becomes a chain. x2, x3, all the way through x100. Okay, and actually I can do efficient inference on this because I can just pass messages along the links. So let's talk about that in some more detail. Basically, we're using the fact that, let's switch this on. We're using the fact that the argmax over all of the variables of the joint is exactly equal to this thing. So if we take out x1, we can push the max over the other variables into the second term. Does that make sense? So we know that we can write the joint of x1 to 100 as conditioned on x1. This is just again the definition of conditional dependence, right? So this has come from, I should probably explain this further, this has come from the fact that p x1 to 100 is exactly equal to x2 to 100 conditional x1 p of x1. Yeah, so now actually I can push this max into that thing, and I can write this. And this is the key insight here, because this is just a chain, whereas this whole thing is a loop. So how do I compute that thing on the right? Well, I can just calculate this thing as a function in x1. And we know that x1 is a binary variable, so it only has two values. So I need to calculate this thing twice for each value of x1. And then I can compare the two and so multiply by this thing. So how do we compute this thing I called f? Well, what is it? Definition of conditional dependence tells us that this is x1 to 100 divided by x, p of x1. But actually, I'm only interested in the maximum of this thing. So I don't actually care what this value is here. So I just need to calculate this for a specific value of x1 twice, because there's two specific values of x1. And then I can answer the question by also looking at the maximum line and multiply it by p of x1.
In the denominator, should it be x2 200?
So I'm conditioning on x1, right?
Yeah.
So this is just definition,
Okay.
just that written another way. Yeah. So I just write the whole function out, which is this product of factors. Right, I'm just going to get rid of this because I'm not interested in the denominator, so I'm just going to say proportional to this thing. That for each value of x1, I'm going to do this, and this thing is equal to x1, which is going to be set to some value, and x100. And what's nice about this is when I take the maximum, which is what I'm interested in this thing, well, I can just push repeatedly the maximum through this whole thing, right? So I can, if I want the maximum of this thing, so I'm interested in the maximum of this. Actually, that's equal to the maximum of this whole thing over x2 to 100. Sorry, this would be R max, right? You know that. We're interested in the arguments here. So the R max over these variables, this thing is the R max over these variables, and this thing. But what I can do, let me point out x1, x100, line up to 1.99. Let's say I take x100, well, I can push that maximum. Actually, 100 was a bad choice, wasn't it? Next to okay, this is fine. So let's say this is going to be the product from 1 up to, I guess, 98, because there's going to be one factor in x100 in here of all these other things. So what I'm going to do is push the max in x100 all the way through this thing. So I've now got the max over x100 here, and this term is in x100. And I have x99. Well, I can just call this some function in x99. So x1 has got a value. And I can just easily do this. So this is the same as passing messages along that chain. So this mu is a message coming along this chain. And so forth. So I get that. This is basically your introduction to message passing along the chain. And the insight is that because conditioning on that x1 means that the thing is no longer connected, I can do this efficiently. I do it for each value of x1, and then I multiply it by this factor, and we should be home and dry. Is everyone happy with that? I guess really, yeah, the whole point here is about the sort of the shape of graphs that you can pass messages along efficiently. And it's difficult to do that when you have a loop. So we're interested in methods of getting rid of loops. And one method of getting rid of a loop is to condition on one of the values, one of the variables. Then you need to do the calculation for each value of that variable, and then you can compute your overall function. So because you were looking a little bit confused, there's a section in the book. Let me write it down on paper. In chapter 5, which is all about efficient inference. Okay, so if you haven't already and you're confused by this question, I would read chapter 5. So it says here the problem with loops. Okay. And then somewhere after this problem with loops. And here's explaining the max product algorithm. So this is the algorithm that we're actually interested in for this particular question, which is passing these maxima through the function, which is what I've just been describing to you. and you define these messages. And this whole question specifically is about loop cut conditioning, which should be explained here. This is for multiply connected distributions, you want some difficult message passing. But if you condition on one of the variables, then it makes your life easier. So it's the point. So if you're confused by this question, I would read first of all problem loops in this section 5.3.2. Okay. So I guess we're running out of time. The next question, I mean, I guess I'll just talk about it a little bit.
Could you put up the other one?
Yep. You have to barely see that, right?
Yeah.
Wait, you want the top? You want this bit? Maybe I'll switch this on. So yeah, here I'm pushing the maximum through the thing, and then defining a message. Yeah, I guess we're running out of time. The next question, 5.3, is about this. You work for a startup company that designs virtual environments in which players can move between rooms. The rooms which are accessible from another in one time step is given in a matrix that he's called M. Maybe I'll do about that and I'll show you the question. So it says, we have this world of rooms. We have a matrix M which has a 1 at a particular point. If we can get from room, the number of the column to the number of the row, which actually looks a lot like the adjacency matrix that we talked about 2 weeks ago. So basically, M is just an adjacency matrix. Probably helpful if they didn't use that word in the question. So yeah, this is basically just an adjacency matrix question. And it says, write a list of rooms which cannot be reached from room 2 after 10 time steps. So if you remember 2 weeks ago, one of the questions was, if I multiply the adjacency matrix by itself, that tells me how many steps it takes to get to each individual room. So if I just multiply this matrix by itself 10 times, that will tell me the number of ways to get to each room after 10 time steps. As I'm interested in getting only to room 2, I just take that column or that row, number 2, it's the same. And that tells me which rooms I can get to in 10 time steps. Basically, I'm not going to get through this in any detail because there's no time left, but I guess Dave can go through it, or I can go through it next time in some more detail. But basically, yeah, the whole question is about that. So, are there any questions? I guess that's probably a more efficient use of the remaining 4 minutes. No? Okay. More like